Okay, so here's a good problem for us. Alyssa, do you want to help us out with this problem? For the following data, determine the order of NO2 in the reaction.
So we have to use experiment 1 and experiment 2 to compare. And, sorry, can I write it down?
Sure. Experiment 1. Experiment 2. What are you writing down?
So I simplified it to make NO2 1 for the first experiment and 2 for the second. And then I had it equal 2 to 1. Oh, you did it the other way. Okay. The rate is 2 and the rate is 4.
Like that?
Yeah.
Okay.
And then the concentration of 1 and 2.
Okay. Very good. And what we're after is that X, right? So what's it mean? Which one is it?
Well, it looks like it would be 2 for experiment 2, but 1 squared isn't 2.
So did I do it wrong? Did I write something down wrong here? We have experiment, we have the, oh yeah, this one has to be 1, right? There we go, 2. Oh, I'm sorry, did I misunderstand what you were saying? I didn't understand, I guess, what you were saying initially, because you said you wrote down 0.00, well, you tell me how to do it again. I'll do exactly what you say this time. Tell me what to write.
Sorry.
That's fine.
So if we do the rate, I put down 2 and 4, but I didn't put it in the decimal form.
Oh, I see. Okay. Okay.
I just didn't put it in the decimal form, and I just skipped to the simplified version.
Okay. But when you do the simplified version, you have to use numbers like 1 and you have to use 1 and 2, right? Because here we are taking some value and doubling it, and here we need to take that same value and double it, right? You could do 2 and 4 here, but you'd have to do 2 and 4 there. All right.
Okay. I can just do the other way. So the rate for NO2 is 0.002, and the concentration is 0.001, and then the rate for experiment 2 is 0.0004, and then the concentration is 0.002.
Okay. Good. So what is that telling us? Can you tell, or do you have to use a calculator?
I think I'd have to use a calculator. I feel like it's like 1/2 or something, but I don't know.
All right. So here is where, I mean, we don't know what the K is. We don't know what the K is. See, 0.001 raised to some value equals 0.0002. 0.002 raised to some value equals 0.0004, but we have a K involved here, right? So if you did use the calculator and worked it all out, it would work the same. But to me, I think it's easier here for us to look and see this is some value. We could call it X, whatever we want to call it. X, for example. This one here is 2X. And these values over here would be just Y and 2Y. Right? And so then we can kind of see what our exponent has to be. Can you tell by looking at that what the exponent has to be?
1.
It has to be 1, right? Another way of looking at it again is to just say our initial concentration is some concentration. We double it. Our initial rate was whatever the rate is, and it doubles as well. Okay, good. All right, so that is good for that. Now, as we said, the rate law and the rate constant for a given reaction, even the same reaction, will differ at different temperatures. All right, the rate laws will differ. Can differ at different temperatures. And the K value is what varies with the temperatures. Okay. Integrated rate laws. If we take a typical progress curve for a chemical reaction, now the term progress curve, it means if I monitor concentration of reactant, let's say here's my chemical reaction, A going to B, simple chemical reaction here. If we monitor the concentration of A versus time, this is called a progress curve. We're just monitoring the progress of the reaction, how the reaction proceeds. All right, and the reaction might proceed something like this. All right, and we would be interested in knowing how much time it's going to take for the concentration of A to decrease, maybe from 100% down to 50%, or maybe down to 10% or something else. All right. For example, if A is a medicine, A is some sort of painkiller, and we want to know how its concentration will change when it's in your system. If this is an antiviral medicine, for example, HIV patients need to make sure that they have always a constant load of the medicine in their system, because if it gets too low, as the concentration of antivirals or whatever the medicine is decreases, then in the case of the antiviral, the virus is going to grow more frequently as that concentration decreases. And so if you get too low, if you overlay the viral load on here, or the viral load will be low, but then it'll slowly start to come up as your concentration gets low. If you forget to take your medication, the viral load can get up past a critical threshold. And so then when you remember to take your medication again and you bring this concentration up to A, if you've taken it too late, your concentration will decrease of your viral load, but it won't decrease down to where it needs to decrease maybe by the next time the medicine needs to be taken. Right? So it's critical to understand how the concentration of one of the reactants, for example, will disappear over time. So you need to know, if my concentration initially is this, what will the concentration be at time X? And what will the concentration be at time Y? We need to have the ability to answer this sort of question. Okay? And to do that, we integrate our rate law. Which is basically telling us, giving us an equation that will allow us to know exactly what the concentrations are at these different time points. Okay? Now, we're going to talk about the integrated rate law equations for 3 scenarios. A reaction where the rate of the reaction is 0 order with respect to the concentration, or to the reactant. We're going to talk about a scenario where the rate of the reaction is 1st order with respect to a reactant, and the scenario where the concentration is 2nd order with respect to a reactant. And we're going to show the integrated rate equations and then use them to predict concentrations at various time points. Let's start off with what's called a 0 order reaction, where the rate is 0 order with respect to the reactant. Okay? So let's look at a general scenario here. Here's a reaction. A reacts to form B. A changes in concentration versus time. It decreases in concentration versus time. Right? So here's A. Its concentration will decrease over time. Okay, nothing new there. But the rate law that describes this is this. Rate equals K with A to the what power? What power do I put here, Alyssa?
I'm sorry, I don't know.
Okay. Well, we said it's...
Is it just like a variable like X?
It's X, but we're talking about a scenario here where it's zero order with respect to the reaction. So that means that the value there is actually 0. Does that make sense?
Yeah.
Okay. Now, this equation, rate equals K, and it's 0 order with respect to X, or A, sorry, 0 order with respect to A. That equation there can be simplified to simply rate equals the rate constant. All right, and Taewon, in this simple reaction there, or rate law, what are our units for K in this rate law? What are the units for K in this rate law, Taewon? That's right. Molar per second. Molar per second. Molar per second. And we knew that because rate is always defined as molar per second. And there's nothing else over here. Okay? So, in a zero order reaction, the rate at which A disappears will be equal to what your rate constant is. It's equal to that value. And that means that that rate is always the same. So you start off with this concentration of A. After a certain amount of time, whatever K is, the concentration will go down. And you'll be able to determine what its concentration is simply by looking at the K. And then again, if you look a little bit later, the same rate influences the reaction, and so you get a linear relationship where the concentration of our reactant A is linearly decreasing with respect to time. All right? And the equation that helps us identify what the concentration will be at any given time, right? So this is concentration of A. What will the concentration of A be at any given time? The equation that can tell us that is this. Our concentration of A at any given time t, all right, A at any given time t will be equal to the concentration of A initially, or A0, meaning at t equals 0, time equals 0, minus whatever your rate of the reaction is, K, times however much time you're going to allow the reaction to proceed. Right? The units here are molar. Right? We would like to know the molar concentration at time t. Units are molar. The units here are molar also. The units for K are molar per second, and the units for T are time, whatever it is. And, you know, if this is molar per minute, then this is going to be minutes. So we see here that the concentration at time t will equal whatever the initial concentration was minus the rate of the reaction, the disappearance, times the time that you allow the reaction to proceed. So that equation, shown here in the slide as well, is our zero-order integrated rate law. Okay? You'll never have to memorize this. It'll be provided for you. You'll have to pull it out of a list. But I think that if you don't memorize it, then you're missing the point. You're missing the learning, the growth, the ability to understand what it means and what's occurring here. All right? Because when we say, hey, here's a chemical reaction, it's zero order with respect to my reactant. So I have a reactant here, A. As time proceeds, the concentration of A is zero order with respect to the rate of this reaction, meaning that the reaction is going to decrease, or the concentration of the reactant is going to decrease linearly. And this line has a slope, Its slope is K, let's call it, right, or whatever you want to call it. We could have given it some other variable, but it's going to be the variable that we use here, so I'm going to call it K. K equals the slope of this line. What are the units for the slope? Taewan already told us it's molar per second. Rise, molar per second, right? So that's consistent, right? And if I want to know the concentration of A at any given time point, I just have to use that slope and subtract it from what I started with, right? So what I start with, we'll call A at time 0, right? And you remove a certain number of molars per second for a certain amount of seconds, and that will tell you how much A you have left at that given time point. Okay, very good. So here's a problem, right? Let's see, whose turn is it? Camille, can you help me walk through this problem here? Rate law for a reaction?
I can try.
Perfect, that's all we need. Rate law for the reaction is zero order. Zero order with respect to A. And has a rate constant of 0.02 molar per second. If the reaction starts with 1.5 molar, how much is present 15 seconds after the reaction begins?
Okay.
So what do we got to do?
Well, the rate is 0.02.
Zero.
That goes first.
0.02 molar per second. Right?
Yes.
That's the rate at which it disappears.
And then starts at 1.5.
Mm-hmm.
Is that mole? Yeah.
Molar, big M.
So A is.
And what do we call that A? What is that? It's a special A. We give it a little number down here to distinguish it.
1.
What's that?
0.
A 0. Because what does that little 0 mean there?
0 order.
No,
I don't know.
that 0 means at time 0. So before the reaction begins, right at the beginning, right? At T equals 0, our concentration equals 1.5 molar, right? So if the reaction starts with 1.5 molar, A, so that's what that means, at time 0. How much is present 15 seconds after the reaction? Okay, so then how do we proceed now?
Well, we have to put it in like the skeleton.
Well, we want to know what A will be at
After 15 seconds.
time T, right? What will the concentration be at time T?
Okay.
And T equals what?
15.
15 seconds. That's right. Well, it's going to decrease this molar for every what?
Second.
Every second.
So that 0.02 over 15.
0.02. I can use the units here to help me, right? So if I include my units, points per second, this is in seconds, right? 0.02 molars for every second. Am I going to divide that by 15?
Multiply it by 15?
Yeah, I'm going to multiply it by 15 because why? What did that do for me when I multiplied it by 15?
It got the second column.
Yeah. And so now that, the answer to this question,
0.3.
all right, is going to be 0.3 molar. And what is that? What did I just solve for?
The molarity at after.
That is how much you're going to lose in those 15 seconds. Does that make sense? Did we do that right? Yeah, okay. Because we started with 1.5, right? So 1.5 is what we started with. We lose that much. So how much do we have when we're done? 1.2. 1.2 molar. Very good. So we took what we started with, that's A naught. We took what we started with and we subtracted the molars per second times time per second, times seconds, to know how much we were going to subtract from our initial concentration of 1.5, and that ended with 1.2. Okay, excellent. Alyssa? No, Sarah's turn. Sarah, can you help me with this one?
Yes.
What do I want to do here?
Okay, so we start with 1.5 molar, so start with that.
1.5 molar equals what? What does that equal to?
That is A sub
A0,
zero.
initial concentration. Okay?
Alright, and then K equals 0.12 molar per second. And then, so we have A sub X, I guess, equals 0.9 molar.
Okay, A sub X, because we don't know what the time is, is 0.9 molar, right?
Yes. So normally we would just plug that in, but I wonder if we have to do something different because it says A reacts to yield to E. Does that matter?
Okay. It doesn't, does it? Because the amount of B is insignificant because it says it's zero order with respect to A, and only the reactants concentrations are going to determine be involved in the rate law.
Okay.
So we just have to kind of look at this relationship. This is how much we start with. True?
Yeah.
So we started with 1.5. We're going to end with 0.9. What do I subtract from that 1.5?
I'm going to have to subtract the rate.
Mm-hmm.
And it'll be the rate times X, which would have been the time.
Okay, very good. So, can we solve this? 0.9 equals 1.5 minus 0.12x. We could solve that, right?
Yes. I got 5 in my calculations.
Is that how we did it? Whoops. Okay. And what are the units for 5? 5 seconds. Very good. Okay, so Alyssa, looking at this one, which of the following is the correct set of units for a rate constant for a zero-order reaction?
I think it's A.
That's right. It's molar per second, right? Because in a zero-order reaction, like we said, rate equals simply the rate constant. There's no concentration dependence on the reactants. Okay, very good. So, a couple of another experiment, another problem there that you can try to work on if you want to. Okay, first order reactions. First order reactions. In a first order rate constant, the concentration of the reactant affects the rate of the reaction. Therefore, if you look at a plot that shows the concentration of A versus time, because the concentration of A influences the rate, first order, right? That means that the concentration of A versus time will decrease, but that decrease will change. The rate at which it changes will slow over time, because as the concentration of A goes down, the rate will also decrease. All right? First order reaction. Okay? So if you look at our equation that relates this reaction, the change D, small d here, the change in the concentration of A with respect to time will equal K times the concentration of A, and integrating this equation results in this relationship here. This relationship here is the concentration of A, concentration of A at time 0, right? Time 0 means the beginning of the reaction, over the concentration of A at any given time, right, time t. This ratio, if you take the natural log of it, it will equal the rate constant times time, all right, times the time. Okay, so let's look at an example here. Radioactive decay of a new atom occurs so that after 21 days, the original amount is reduced to 33%. What is the rate constant for the reaction in per seconds? Per seconds. Now, the rate constant for this reaction, right? Let's write what the rate law will look like. The rate law is going to be rate equals K, but now we include the concentration of A, and we could put the 1 up there if we want to. So there's our rate law, and we can see for this rate law, the units of K are going to be different than it was for the zero order reaction. Whose turn is it? Is it Alyssa? I think it's Alyssa. Well, tell us, Alyssa, what's the rate, what's the constant, or what are the units for the K in a first order reaction like this?
Are they the same as the zero order?
Is it? What's the units for the rate? Rate is always what?
It's always mole per second.
Very good. And A here is now what? What does it contribute to our rate law?
Is the concentration of A include the A0 and the AC? whenever we're simplifying that equation?
This one here?
Mm-hmm.
Nope, that concentration, that A right there just is the concentration of A. So its units are going to be the way we express concentration, which is molar.
So that equation is just like how it is right there. It's not meaning the ln.
No, that's right.
Okay.
This is the non-integrated. This is just the rate law for a first order reaction.
Oh, okay.
And what we're trying to do,
So it would
yeah,
have to be 1 over seconds.
that's right. The units for K here would have to be 1 over seconds. And that's the way it is for any reactant that is first order, right? The K for that reaction will be 1 over seconds. And that's what it says here. What is the rate constant for the reaction in units of 1 over seconds, or seconds to the negative 1, which is the same thing. So in this scenario here, what we're going to do is we're going to take our integrated rate law, which is the natural log of my initial concentration over my concentration at time t, and see that that equals K times T. Okay? What values could we put in here for this reaction, Alyssa, for this problem? What values could we put in A0 and AT for this problem?
Well, for the time it's been 21 days. Does it have to be in seconds? Do we have to, like, multiply it to find it in seconds?
Yeah, I guess we do, don't we? Because they ask us to in the end. So let's do that. 21 days times 24 hours times 60 minutes times 60 for seconds. Is that right? Did I do that right?
Yes, sir.
24 hours, 60 hours, or 24 days, 60 hours. 21 days, 24 hours, 60 seconds, 60 minutes, 60 seconds. Yeah, okay. So 1.81 times 10 to the 1, 2, 3, 4, 5, 6. So there's my seconds. K is what we're trying to identify, right? So what can I use for the rest of this equation here to finish it up? What do you think, Alyssa? What?
Well, we know how much the original amount is reduced, so we can put that in decimal form and use it.
Okay. So what would I put, like, for example, the initial amount, 100%? Is that what you're thinking? And
I
now,
was thinking, yeah, sir.
and now I'm down to 33%. Would that work?
Mm-hmm.
Okay. So, what value is that? 100 divided by 33, 3.03. If I take the negative or natural log, oops, that's not it. The clear. Oops, natural log of, what was it? 3.03. Is that what I said? Let's make sure here. Yeah. So the natural log of 3.03, 1.1. So we got 1. Well, I'll use it up here. This business on the left equals 1.109. And then that equals K times 1.8 times 1.81 times 10 to the minus 6. So now I just have to take my 1.1085662 and divide it by 1.81 times 10 to the 6th. So that gives me 6.12 times 10 to the minus 7. Okay. So again, this equation would be provided for us, but we're going to talk more about this equation to help us realize how we can kind of envision it a little bit better, because it's a little more cryptic by itself initially to start off with. But it being provided for us, we can put it into 21 days, solve for it in days, and then convert that to seconds. 6.1 times 10 to the minus 7. Let's talk more about this equation here, this first order reaction, and recognize something interesting. Okay? A first order reaction is also what is occurring when we talk about a half-life for a process. Now, half-lives are generally, has anybody heard of half-lives before? Say yes if you've heard of half-lives before in the chat box. Half-lives pertain to what, Sarah? Where have you heard of half-lives before?
Just in textbook problems, you see them a lot.
Okay. Do you remember what half-life means?
It's something like the amount of time it takes for something to decompose.
Half the way.
Yeah.
Right? Very good. And nuclear reactions or nuclear material all have half-lives, meaning that if you start off with X and it takes 10 days to go from X to half X, it'll take an additional 10 days to go from half X to quarter X, like this plot is showing here. Right? We have initially an initial concentration of some material, and then after a half-life, the amount of time it takes to decrease it down to halfway, half its concentration, right? It will then require another half-life to go down to half of what its concentration was after the first half-life. All right? So you can see that it's concentration dependent because the rate at which it disappears slows over time. The first section here, you got rid of 50% of the material, but after the next 8 days, you didn't get rid of 50%. You only got rid of 25%, right? And then here you only got rid of 12.5%. Okay? So there is this relationship where at time t, the concentration will, where t is your half-life, the concentration of A naught will always be half as much. Let me rewrite that so we can see that clearly. A after t half, where t half means the half-life, will equal A naught over 2. A naught over 2. So what's interesting about that is if we take our integrated first order reaction and we input this information for t where t is your half-life, then what you get is, let's talk about why this happened. Here, the initial concentration, and here, down here, is the initial concentration divided by, or cut in half. Sorry, not divided by, but cut in half. And if you put this divided by this, it's basically multiplying by 2, right? So the natural log of 2, because these drop out, will always equal K times your half-life. All right? So the natural log of 2 for any given first order reaction, that value, which is a fixed value, the natural log of 2 is a known number, will always equal your half-life sorry, not your half-life, but your K value times your half-life. All right? So there's a little bit of power there because the natural log of 2, again, is just a value, right? And the natural log of 2 is just a value. Now, the natural log itself means the log of E, the log of Euler's number. And Euler's number is a number that we see in growth and decay of populations that follow a first-order trend like this. Kind of like the value pi. Pi is a relationship between the diameter and the circumference of any circle you draw, right? And there's a whole class about that, right? That's trigonometry, right? Well, Euler's number is a number that relates the growth over time of a given population to a first-order operation. So, again, there's power in recognizing that this number, natural log of 2, 0.693147, which you can always type in, will always equal the rate constant for a first-order reaction times the half-life of that reaction. Okay? So, the natural log of 2 divided by our rate constant will always be the half-life. The natural log of 2 will equal the rate constant times the half-life, or the natural log of 2 divided by the half-life will always equal our rate constant. So here it is. The half-life for this chemical, this iodine 132, chemical is not the right word, it's called a half-life for this isotope. The half-life for the isotope iodine 132 is 2.295 hours. What percentage remains after 24 hours? All right. For this one here, we want to use our integrated rate law, where we say the natural log of our initial concentration over our concentration at time t, right, is equal to K times T, all right? And if we have allowed the reaction to proceed for 24 hours, time T, multiply that by that, we want to know what percentage of our material remains. So if we said, for example, 100 over X, this would be the amount of material that would, the percentage of material that would remain. So we need to solve for our X. The only thing we're missing here is our K. How can we get the K? Well, we can get the K by knowing that the natural log of 2 divided by our half-life will equal, well, so let's just do it this way first. Natural log of 2 equals K times our half-life. So then we can divide both sides by our half-life. And there we can see the natural log of 2 divided by our half-life should equal our K for this reaction. So, natural log of 2, that's already in my calculator, divided by our half-life, 2.295, gives us our K of 0.302. So we use that up here, 0.302 times our 24. This is in per hours, right? It's 1 over time. This is in hours. right? And then that will equal the natural log of 100 over x. Okay, I'm going to rewrite that equation here on a fresh piece of paper to give us a little more space. We have a little bit of conversation about math here. Natural log of 100 over x equals 0.302 times 24. There's the equation I need to solve there. I can simplify our right side of the equation really quick here. 7.248. All right, equals natural log of 100 over x. Little algebra reminder of how to solve this sort of problem. The natural log of 100 over x can be rewritten as the natural log of 100 minus the natural log of x. So log of a over b is equal to log of a minus log of b. Log of a times b is equal to log of a plus log of b. All right, so this here, natural log of 100 minus natural log of x equals 7.248. Okay, so now I can type in 7.248 and subtract that from the natural log, or take 7.248 and subtract from it natural log of 100. And that's going to give me 2.6432. Okay, so I have to keep that minus sign. Negative natural log of x equals 2.643. And then I have to divide both sides by -1, so the natural log of x will equal negative 2.643. Okay, so then in my calculator, I put to identify what x is when I have the negative natural log of x equaling 2.643, negative 2.643, second natural log negative 2.643, and that gives me my x here, which was my 100 over x, or in other words, the percentage that's left over.